Hey Technostuds! To create a ciphertext or an encrypted message, you're going to need to have a message that you want to encrypt. You're going to need to know the cipher or algorithm that you're going to use to encrypt that, and then you're going to need some sort of key to encrypt it and decrypt it. A big part of how secure your ciphertext is going to be that key. And specifically, it's going to be about the key length. So in this video, let's talk about cryptographic keys and the key lengths and what that looks like. In the next set of examples, we are just going to convert the word secret into a ciphertext. And we're going to use a key of 8. What that means is that we've just shifted over this alphabet in this bottom row by 8 places. So now this S is going to become an A. And so we have an A there. This E is going to become an M. So we have an M there. This C is going to become a K. So we have a K there, and we've converted this. Of course, this makes it really easy to hack this message because all we have to do is we can see that M is repeating itself, and there's a good guess that that's going to be the letter E. And from there, we can reverse engineer this and figure out what our actual plain text is. So this is very easily crackable with only a key of 8. To make this message more secure, what we can do is we can add a bigger key. We're using the same algorithm, the same cipher, to encrypt the message. What we're doing is we're just using a larger key to do it. And what we're going to do is we're going to take that first number, which is 8, and this first table shows that we've shifted the letters by 8 places. Then we take the second one, which is going to be shifted by 2 places. And then we'll just alternate between these. So the first letter, we'll use the first table. The first letter is S, so the S becomes an A. Then we're going to use the second table, which has an E, which is on the second table is going to be a G. We go back and use the first table again, which is a C, and a C is a K. And then we use, for the fourth letter is R, so we're going to use the second table again, and R becomes a T. And then we have another E, but this time we're using the first table for this E, so that becomes an M. And notice that our 2 E's now are 2 different letters. We've just drastically increased the security of this by adding a second number to this. So it made a huge difference, although it's still pretty easy for a computer to hack this. As you imagine, if we make our key even longer, we've added more security. Now we have 3 tables, and the first letter will use the first table, the second letter will use the second table, and the third letter will use the third table, and we'll start it all over again. And therefore, we will make a much more safe ciphertext with this that's going to be much harder to reverse engineer and figure out what the plain text is. The keys on your computers are actually going to look a little different. Computers use binary numbers, so we measure these keys in how many bits, and a bit is either a 1 or a 0. So in this case right here, we've got 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 positions here. Here we have 10 positions, so 3, 4, 5, 6, 7, 8, 9, 10. Every time we add a bit to a key, we actually double its complexity and make it that much harder to figure out what the key is going to be. So let's take a look at what that looks like. It's the powers of 2. So we start out with 1 bit. A 1 bit can either be 2 possibilities from a computer standpoint. It's either a 0 or a 1. So there's 2 different states. When we go to 2 bits, we actually double that to 4 possibilities. We got 0, we've got 1, we got 1, 0, and 1, 1. Now let's add another bit and we double it again. Now there's 8 possibilities. So we could have 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. The equation to figure out how many possibilities there are with bits would be 2 to the however many bits you have. So for instance, 8 bits is 2 to the 8th power, so you have 256. 9 bits is 512. 10 bits is 1024. 11 bits, 2048. 12 bits, and you can get the picture, it doubles every time and gets drastically larger. So the question is how many bits do we need in our key to create a secure ciphertext? Or another way to ask that question would be what can computers crack? What type of keys can they crack and how big are those bits? So the answer actually changes over time because the computers nowadays can crack things that we couldn't crack 10 years ago. So we can take a look at history and see what's happened. So with DES was an acceptable standard that a lot of people used and said this is what we're going to use as the standard for encryption. It was 64 bits. It was adopted in 1976. That's when they said this is the approved standard. Even though it was 64 bits, effectively it was 56 bits because there's some parity bits in there. So if we figure out how many possibilities that key has, it's 2 to the 56th power, which ends up being this number. That's 720 followed by 14 zeros. So that is an incredibly large number. I'm not going to write all of the zeros out because it's a lot of zeros. I mean, this is a huge number. That's how many possibilities there are. So it wasn't until 1997 when it was first cracked. It was cracked again in 1998 from a computer that cost $250,000. Another 8 years after that, then it was cracked by a machine that only cost $10,000. And in 2016, just by a standard graphics card that you could buy off the shelf. So our computing power got better and better. So what is the standard now? Well, AES was accepted as the alternate status or the alternate way of encrypting. That was accepted in 2001 is when it became the new standard. And it has actually several settings, 128, 192, 256. And so it actually has different numbers here, 36 zeros, 55 zeros, and 75 zeros. So you can see pretty complex, especially compared to the DES right here. So these are, and one of the questions you might ask is, well, why don't we just always use 256? I mean, that's the most secure. It's got the most digits in it. So why don't we just always use 256? Well, there is processing load. And so what happens is that if you're encrypting everything at 256, you might be just spending a lot of extra time and a lot of extra energy in encrypting things that's not necessarily needed. That 128 might be secure enough for you. So it changes over time, and we also have to have other considerations like how long is it going to take, what's the processing load that it's going to be, and how much delay is there because you're encrypting things. So that brings up an interesting point. Whatever key you create will probably be able to be cracked at some point in time. However, there is one exception to that, and it's a theoretical exception. And that is that there is a one-time pad that theoretically can't be cracked. So what does a one-time pad look like? Well, it follows several rules. A one-time pad is a key that must be just as long or longer than whatever plain text it's encrypting. So we're talking about a really long key if you've got a really long plain text. The key must be completely random. And there's actually quite a few like subtopics to this right here of what is completely random and making sure it's evenly distributed, and there's quite a bit that goes into even defining that. It must never be used again, and it must be kept completely secret. And then if these are followed, then theoretically you could create a key that is uncrackable.